Hello everyone, today we're gonna learn how to find the areas between the curves by using integrals. So let's get straight into it. Let f of x be defined as that polynomial and g of x that function. Let R and S be the two regions enclosed by the graphs of f and g as shown in the integral. So this is our f function, this is our g function, and we need to find the areas between these two curves from x equals -2 to another intersection. There are three intersections here, not two intersections. There are some scenarios where there are only two intersections, and it's relatively easy to figure out the answer in that case. So you can have something like that, and then they tell you to find the areas between the curves. You basically take the integral of this bigger function with respect to x-axis. I mean, you basically take the integral from a certain x value to another x value between the function and x-axis, and you do the same thing for this function, and then say from 0 to 5, and bigger function is f of x, this is my 5, sorry, dx, you have to subtract the integral from 0 to 5 of g of x dx, where g of x is this smaller function. When there are only 2 points of intersection, like that point and say that point, it's easy to find the answer because you can say f of x is equal to g of x, and then you find those two x values, and then you put in those values as your bounds of integration and you get the answers. But here it's not so simple, because they're telling us that there are 3 points of intersection. So we need to find this one, and then the question is, find the sum of the areas of regions R and S, as I told you already, using a graphing calculator, and round your answer to 3 decimal places. So they allow us to use the calculator because look, if you try to find all these 3 x values yourself, here, here, and there, you of course will be able to do that, but it's going to take too much time. So f of x is x cubed plus x squared minus 6x. This should be equal to -4x over x plus 3. So you multiply by x plus 3, then you get f of x, and here times x plus 3 is equal to -4, and here you have the fourth power, and then you have cubes, and you have squares. It's basically too complicated. That's why they're telling us that we can use graphing calculators, but here we're going to use the graphing calculator only to find this x value so that we know what the bound of integration should be. Well, first of all, let's try to understand what should be the mathematical equation we need to figure out the solution to in order to get this question correct. So we can say that we first need to figure out the area between g of x and f of x from -2 to 0. So that's going to be the area. That's going to be the area of f of x. Note that f of x is simply greater than g of x here. That's why we're telling f of x minus the area of g of x, because f of x is higher. From -2 to 0, f of x is higher, that's why we're subtracting. So if you find the value for this expression, this is going to be equal to r. Maybe it's not really visible to you. That's r and that's s. Alright, then this is r. Let's find r. Right now, we don't really need to know what is this third x intersection. Let's just focus on this expression only. So if we plug in the values for f of x and g of x, we get the integral from -2 to 0 of x cubed plus x squared minus 6x, don't forget your dx, minus the integral from negative 2 to 0 of negative 4x divided by x plus 3 dx. This part is pretty easy. Just the reverse power rule, x to the fourth power over 4. So if you take a derivative of it, you'll get 4 here, and when you're going to subtract your exponent by 1, so you're going to get x cubed. You already need to know that at this point. So x to the fourth power over 4, plus the same thing with the second variable now expression, x cubed over 3 minus 3x squared. And we're gonna evaluate it, add 0, and subtract our evaluation at negative 2. Now the same thing with this part. First of all, let's just use the algebraic long division to set it up as the sum of two variables. So what I'm talking about. Look, if you have any polynomial divided by another polynomial, say x cubed plus x over 4x plus 6, you can set it up as 4x plus 6, which is in the denominator. How many times does it go into x cubed plus 3? And from there you solve for it. You say, oh, it goes 1/4 x squared, and then you plug in these values. That's basically the idea behind long algebraic division. Let's do that division for this variable right here. So in the denominator we have x plus 3, so we're going to put it there, divided by 4, no, look, negative 4x divided by x plus 3, because this is in the denominator and this is in the numerator. So how many times does x go into negative 4x? Well, negative 4 times. And then we need to multiply both of these by negative 4x and subtract it, the value of it. So negative 4x times x is negative 4x. Negative 4 times 3 is negative 12. So these values cancel out and we get plus 12. And if there's a remainder, then you basically do plus the remainder and the function that you were dividing by in the first place, which in our case was x plus 3. So this is our alternative for this hairy one. So minus the integral from negative 2 to 0 of negative 4 plus 12x plus 3. I'm taking it straight out of here. Let me get rid of it now. This is equal to r. Don't forget, we're solving for this part of the problem, because there are two parts. Then we're going to calculate s as well. So what is this going to be? If you plug in 0 here, all the values are going to be 0, and then we need to subtract the values when you plug in negative 2. So negative 2 to the fourth power is 16 over 4. Negative 2 to the third power is 8, so negative 8/3. Negative 2 to the second power is 4. 3 times 4 is 12. And here, the antiderivative of negative 4 is quite simple. It's just going to be negative 4x. The antiderivative of 12 over x plus 3 is going to be plus 12, the natural log of the absolute value of x plus 3. And this is also evaluated from 0 to negative 2. This is r, don't forget. So what do we get here? This is 4 minus 12 here is going to give us negative 8. And then we have negative sign here, so it's going to be positive. Negative is positive, so 8 plus 8 over 3, and now this part is left. So if we plug in 0, we get 0 plus 12 the natural log of 3 minus the function evaluated at -2. -4 times -2 is 8 plus 12 natural log. -2 plus 3 is 1. The natural log of 1 is just 0. 12 times 0 is 0, so we get 8 on this side. 8 plus 8/3 minus 12 times natural log of 3, just minus 8, because here we got just all zeros. They cancel out. So the very last expression we got left is 16 plus 8/3 negative minus 12 times natural log of 3. Now let's use a graphing calculator to quickly evaluate it. I'm not going to give the exact value because there will be many decimals right there, but I'm going to give a quick approximation. So 16 plus 8/3 minus 12 times natural log of 3, we get 5.4833. This is R. And recall that R is only this part of the function. Now we have to find S. So how do we find S? Well, you need to understand that here in this interval, x interval, now f of x is no longer above g of x. G of x is above f of x. So our expression is going to look a bit different. So we're going to have the integral from 0 to this third intersection, let's call it just, I don't know, g for now, of g of x, because g of x in that x interval is higher and greater than f of x, minus the area between the same bounds of f of x times g of x. The logic behind finding the areas between the curves is simply that if you let's look at this part. I'm gonna just get rid of everything. The logic behind it is that if you evaluate the area between f of x and x-axis within this x interval, you get all of that. And when you subtract the area between the second curve, which is g of x, and the x-axis, you get all of this. So the area that's left is exactly what we're solving for, which is the area between these two curves. The same logic applies here. So we get the area between g of x, here g of x, and the x-axis, so it's that, it's already negative, minus the area from f of x to x-axis. So this minus this is going to give us a positive value, because our blue part right now is a negative, let's call it k, this area is k, and then in our equation we're subtracting another negative value, let's call it c, this is c. And since c is greater than k, like visually it's pretty obvious, the final value is going to be positive. It's going to be, so S is going to be positive, which makes sense. So let's go ahead and evaluate it right now. Let me quickly get it over here. All right, so now let's use our graphing calculator to understand what is D. D is basically the third intersection here. Let me do it real quick. So f of x is equal to x cubed plus x squared minus 6x, and g of x is equal to negative 4x over x plus 3. So the first intersection is at x equals negative 2, the second is at 0, and the third is at 1.82843. So d is equal to 1.82843. 1.82843. The same thing here. So what is this equal to? So the integral from 0 to 1.828.843 of g of x. What is g of x? It is negative 4x over x plus 3. What was that? Dx minus the integral from 0 to that same d. F of x is x cubed plus x squared, x cubed plus x squared minus 6x dx. Now note that we already found the antiderivatives of f of x and g of x, but now we're just evaluating them at different x points. So let's just find what the antiderivatives were. Here, this is our antiderivative of x, and this is our antiderivative. No, wait, this is our antiderivative of g of x. So here, the antiderivative of that will be, let me pick another color. It will be negative 4x plus 12 times ln x plus 3 evaluated at 1.82843 and subtracted from 0. This minus, here we have the antiderivative of f of x, so let's just paste it. Evaluate it at those same bounds. All right, so what do we get here? Let me use a calculator to plug in this to each x, because it's really gonna take too much time if I do it manually. So we have g of x at 1.82828.3. That is equal to 1.8284. No, I'm sorry. It's equal to 11.5805. Then minus the function value at 0. This is going to be 0, and this is going to be 12 times natural log of 3. And then we have the second part of the expression. Again, I'm going to use a calculator to evaluate it. This is going to be negative 5.1977 minus the function evaluated at 0. It's going to be all 0, so we're not going to write anything there. And now when we add this, what do we get? 11.5805 minus 12 times natural log of 3 plus 5.1977. We get 3.59 5. And note that this is S. We were solving for this part. The area between the curves in this X interval. Now we get a little bit of a drum roll here. R is equal to what? Let me copy it. R is equal to this value right over there. Then S is equal to this value right over there. So R plus S, which is exactly what we were solving for. Here it says, find the sum of the areas of regions R and S. This is equal to 5.4833 plus 3.595 equal to, look, it says also round your answer to 3 decimal places. So let me pull up my calculator. 5.4833 plus 3.595 gives us 9.078. That is your final answer. And what does it mean? What is it saying? 9 units squared. It's actually the area, so it's going to be units squared. But since we're not given units, I'm not going to write that. This basically tells us that the area between these two curves from -2 to 0 plus the area between these curves from 0 to this 1.5 whatever we found is equal to 9.078. I hope it really helps. I hope now you will leave this lesson with more clarity about integrals and applications of integrals. And thank you for your time.